Right now, 63 light-years from Earth, a young star is shining through a storm of dust, shattered rock, frozen debris, and unfinished planets. For decades, astronomers have watched this system because it looks like a younger version of our own solar system, caught before the construction dust has settled. They knew two giant planets were there. They mapped the disk around them. They measured its strange edges, its warped layers, its clumps, its gaps. And still, something important was missing. Then the James Webb Space Telescope found it. Not as a clean photograph, not as a bright dot waiting politely in empty darkness. Webb found the hidden world as a chemical barcode buried inside the glare, a pattern of carbon monoxide lines appearing where scientists expected only smooth light scattered by dust. The signal was faint, but it moved with the star. It sat inside the debris disk. It occupied a region where earlier images had seen confusion, noise, and fog. The planet is now called Beta Pictoris d. It is probably at least twice the mass of Jupiter, orbiting roughly as far from its star as Neptune orbits the Sun. Yet it remained concealed inside one of the most studied planetary systems in the sky. Picture a grain of pepper hidden inside the beam of a stadium floodlight, then place both objects 63 light-years away. That is the kind of contrast Webb had to defeat, but the discovery creates a deeper puzzle. How did a planet that large remain unseen? Why had astronomers already suspected that something occupied its orbit? What does its atmospheric fingerprint reveal about the way giant worlds form? And how many other planets are hiding inside bright disks, invisible not because they are too small, but because we have been searching for them in the wrong way? Almost nobody outside astronomy realizes what has changed here. Webb did not simply add one more planet to a catalog. It demonstrated a new method for finding worlds inside cosmic fog. Stay with me, because by the time this is over, you will never think about an empty patch of starlight the same way again. Before we go further, subscribe and turn on notifications. Discoveries like this rarely arrive as simple answers, and the next signal hidden in the data may be even stranger. Let's go back to the beginning. On October 6, 1983, the infrared astronomical satellite detected an unexpected excess of infrared radiation around a bright star in the southern constellation Pictor. The star was Beta Pictoris, visible to the naked eye from dark southern skies. At the time, astronomers were not expecting to find a planetary system. They were studying stars and infrared sources. What they found instead was evidence of warm material surrounding a star. A year later, observations from the Las Campanas Observatory resolved a disk of dust seen nearly edge-on. That image changed Beta Pictoris from an interesting infrared source into something far more important, a laboratory for planetary formation. The original expectation was modest. Young stars should be surrounded by leftover material. Planets form inside disks of gas and dust, so a dusty disk around a young star was not impossible. But Beta Pictoris did not behave like a simple, smooth ring. Its disk was bright, extended, asymmetric, warped, and full of structure. Later observations reveal belts, clumps, inclined components, and a sharply defined inner region. The system is only about 23 million years old. That sounds ancient by human standards, but for a planetary system, it is childhood. Our Sun is about 4.6 billion years old. If the Sun's lifetime were compressed into a single day, Beta Pictoris would be only minutes into the morning. And the comparison matters, because Beta Pictoris offers something astronomers almost never receive: a view of giant planets and debris interacting while the architecture of a system is still being shaped. Beta Pictoris b was identified in direct images from the European Southern Observatory's Very Large Telescope. A second giant, Beta Pictoris c, was first detected through the star's tiny radial velocity wobble and later directly imaged. By then, astronomers had two planets, a famous debris disk, and decades of observations. It looked like the main cast had been identified. It had not. Here is where the first twist arrives. The newly discovered planet was not the target. A team led by Aidan Gibbs at the University of California, San Diego, was using Webb's near-infrared spectrograph, or NIRSpec, to study the atmosphere of Beta Pictoris b. NIRSpec does not merely take a picture. It spreads light into a spectrum, separating wavelengths the way a prism separates white light into colors. Molecules absorb specific wavelengths, leaving dark or bright features that act like fingerprints. The team used NIRSpec's integral field unit. If you have never heard that term before, think of it as a camera that gives every pixel its own miniature rainbow. Instead of recording only where light appears, it records what that light is made of at thousands of positions across a scene. That distinction is the entire story. The expectation was that Webb would characterize a known planet, while the surrounding debris disk produced a smoother background of scattered starlight. But in the data, away from Beta Pictoris b, another pattern appeared. It was not smooth. It contained a sequence of peaks and troughs, a repeated molecular signature associated with carbon monoxide in the atmosphere of a giant planet. A bright blob by itself would not have been enough. Astronomers are trained to distrust blobs near bright stars. Instrumental artifacts can imitate objects. Dust structures can imitate objects. Data processing errors can imitate objects. A feature may appear in one image and vanish when the telescope rotates or the analysis changes. But a molecular spectrum is harder to fake. The carbon monoxide pattern did more than identify chemistry. Because the lines were shifted by motion, they also carried velocity information. This is the Doppler effect, the same basic phenomenon that changes the pitch of an ambulance siren as it passes you. Light from an approaching object shifts slightly toward shorter wavelengths. Light from a receding object shifts toward longer wavelengths. From that shift, the team could test whether the source belonged to the Beta Pictoris system or was simply a background object lined up by chance. Its speed fit, its position fit, its alignment with the disk fit. The hidden source was orbiting Beta Pictoris. According to the discovery study published in the astrophysical journal Letters, this made Beta Pictoris the first directly imaged planet discovered primarily through moderate-resolution spectroscopy. That phrase sounds technical, but the meaning is simple. Astronomers found the planet by recognizing the chemistry of its atmosphere before they trusted its appearance. Not by shape, not by brightness alone, by a barcode. Stop and sit with that. Webb was pointed at one known world, and the atmosphere of another world announced itself from inside the dust. Now the story gets stranger. Beta Pictoris is not an obscure star that astronomers had barely examined. It is one of the most intensely observed young planetary systems in the Milky Way. Ground-based telescopes, space telescopes, infrared instruments, optical cameras, spectrographs, and coronagraphs have studied it for decades. A coronagraph blocks a star's central light, like holding your thumb in front of the sun, but scattered light remains. In Beta Pictoris, dust redirects the star's light into a glowing fog exactly where a planet may be hiding. The expectation was that a giant planet at a wide orbit should eventually show up as a point source in high-contrast images. Instead, Beta Pictoris d remained blended into the disk. To put that in perspective, imagine trying to identify a dim lantern through a windshield covered in sunlit mist. The lantern is real. It may even be relatively large, but the background is not empty. Every droplet scatters light toward you, erasing the clean contrast your eyes need. Traditional imaging asks, is there a point of light here? The new approach asks, is there a planetary molecule here, moving at the correct speed? That is a much more selective question. Webb effectively ignored much of the dust because the dust did not carry the same narrow carbon monoxide signature. The disk was bright, but chemically broad and smooth. The planet was faint, but spectrally precise. This is why the discovery is more than a lucky surprise. It reveals a way to separate planets from environments that defeat ordinary imaging. Young planetary systems are messy. They contain dust, gas, collisions, hot material, and structures carved by gravity. Those are exactly the systems astronomers most want to study because they preserve the evidence of formation. They are also among the hardest places to see planets. Webb turned the difficulty into an advantage. The disk can hide the planet's image, but it cannot easily hide the planet's atmospheric fingerprint. And there is another reversal. Long before Beta Pictoris d was confirmed, astronomers had reason to suspect that an unseen planet might exist in roughly this region. The inner edge of the debris disk is unusually sharp. Other structures in the disk also seem sculpted rather than random. Planets can act like gravitational shepherds, clearing unstable orbits, trapping debris into patterns, and maintaining boundaries that would otherwise blur over time. Think of a hidden snowplow moving through a wide field. You may not see the machine behind the storm, but you can infer its path from the clean edge it leaves behind. Beta Pictoris d may be that hidden sculptor. Models place it at roughly 30 astronomical units from the star. 1 astronomical unit is the average distance between Earth and the Sun. 30 astronomical units is comparable to Neptune's region in our solar system. The planet is estimated to be at least twice Jupiter's mass, making it the smallest of the 3 known giants in the Beta Pictoris system, though smallest is doing a lot of work there. 2 Jupiters contain more than 600 Earth masses. The first contradiction, then, is that a massive planet remained visually concealed. The second is that its gravitational influence may have been visible before the planet itself. And the third is that the instrument revealed it while doing something else entirely. But none of that prepared researchers for what this method implies about the planets we have already missed. For most of the history of exoplanet science, astronomers have found worlds indirectly. Transits measure a star's dimming. Radio velocity measures its wobble. Microlensing watches gravity bend background light. Direct imaging separates a planet's light from its star. Each method has biases. Transits favor planets whose orbits line up edge-on from Earth. Radial velocity favors massive planets close to their stars. Direct imaging favors young, hot, massive planets far enough from their stars to be separated in the sky. No method sees everything. Beta Pictoris d occupies an especially difficult category. It is young and massive, which should help, but it sits inside a bright debris disk, which hurts. It orbits far enough out to shape the disk, but its environment floods ordinary images with scattered light. The new spectroscopic method changes the selection rules. A planet does not need to stand out as a perfect dot if its atmosphere contains strong, identifiable molecular lines. In principle, astronomers can search data cubes, three-dimensional collections containing two directions on the sky plus wavelength, for molecular patterns moving at orbital speeds. It is similar to finding a single voice in a crowded room. A photograph of the crowd may not tell you who is speaking, but if you know the voice's exact frequency pattern, you can isolate it from the noise. Here is where the second major finding becomes larger than the planet itself. Webb did not simply see through dust. It demonstrated that chemistry can function as a discovery tool. This was the first directly imaged planet found primarily through moderate resolution spectroscopy rather than conventional imaging alone. That matters because atmospheres are not decorative layers. They record temperature, gravity, formation history, cloud structure, and chemical processing. Carbon monoxide is common in hot giant planet atmospheres, but the strength and shape of its absorption features depend on pressure, temperature, composition, and motion. With more observations, researchers can refine Beta Pictoris d's temperature, atmospheric properties, mass, and orbit. And because Beta Pictoris is so young, those measurements can test competing models of how gas giants are born. One model is core accretion. Dust grains collide, build larger bodies, form a solid core, and then pull in surrounding gas. It is a bottom-up process. Another is disk instability, in which a region of the gas disk collapses rapidly under its own gravity, more like a small version of star formation. Both pathways can produce giant planets under the right conditions. The challenge is determining which occurred in a specific system. A planet's mass, luminosity, atmosphere, and orbital position can preserve clues, but those clues evolve. Young planets cool, clouds change, gas mixes, orbits interact. The earlier astronomers observe them, the closer they are to the original event. Beta Pictoris is therefore not just a planetary system, it is a crime scene that has not yet been cleaned. 3 giant planets now orbit inside the debris disk. Their masses and distances can be compared with the disk's structure. Their atmospheric chemistry can be compared with one another. Their orbits can reveal whether they formed where they are or migrated after birth. Picture 3 heavy boats moving through a harbor filled with floating leaves. The patterns in the leaves record where the boats have passed, but only if you can identify every boat. Miss one, and the entire wake pattern may seem impossible. For years, Beta Pictoris d was the missing boat. Its discovery may help explain the sharp inner edge of the disk and other puzzling features. But may is important. The orbit is not yet known precisely enough to declare the case closed. Researchers still need additional observations to measure how the planet moves over time. They need better constraints on its temperature and atmosphere. They need to test whether its gravity can reproduce the disk structure seen in images. Science does not become weaker when the answer remains incomplete. It becomes honest. And right now, the honest conclusion is that the planet fits a long-standing suspicion, but its full role is still being worked out. Here is where the third major finding arrives. The Beta Pictoris system is now only the second known planetary system with at least 3 directly imaged planets. That makes it exceptionally valuable. In our own solar system, we can study 8 planets in detail, but we see them after billions of years of evolution. Around other stars, multi-planet systems are common, yet direct images of multiple worlds are rare because the contrast problem is brutal. With Beta Pictoris, astronomers can watch a young system as a connected machine. Beta Pictoris b orbits closer in. Beta Pictoris c is also relatively close to the star. Beta Pictoris d occupies the widest known orbit of the 3, near the inner boundary of the debris disk. Their gravitational interactions may influence their long-term stability. Their positions may reflect migration through the original gas disk. Their atmospheres may reveal whether they formed from the same material at different distances or followed different paths. The expectation, before Webb, was that the 2 known giant planets explain much of the system's architecture. The contradiction is that the disk still contains signatures suggesting additional structure, and spectroscopy revealed a 3rd giant hiding in plain sight. Plain language version: the map did not make sense because one of the largest objects had been left off it. When the unexpected bright source appeared, the researchers did not immediately announce a planet. They questioned it. Jean-Baptiste Ruffiot, the principal investigator of the first Webb observations, explained that bright blobs can be instrumental artifacts or pieces of the debris disk. The team relied on the simultaneous spectrum to test the source. That caution is not hesitation. It is the mechanism that makes a discovery trustworthy. First comes the anomaly, then suspicion, then every attempt to make it disappear. Could it be a detector effect? Could it be scattered light? Could it be a background star? Could it be a brown dwarf unrelated to the system? The spectrum, velocity, position, and disk alignment narrowed the alternatives. Separate observations using the European Southern Observatory's Very Large Telescope and Webb's near-infrared camera independently supported the planet's existence. Only after the signal survived those tests did the hidden world become Beta Pictoris. Real discovery often looks like this: several instruments, different teams, repeated measurements, cautious language, and a pattern that refuses to go away. Still orbiting, still imprinting molecules into light, still reshaping the debris around it. Here's the part that stops being abstract and starts being personal. Every atom in your body came through a history of cosmic construction. The carbon in your cells, the oxygen you breathe, the calcium in your bones, the iron carrying oxygen through your blood, those elements were forged in stars and recycled through clouds of gas and dust. But elements alone do not make a habitable world. They must be assembled into a stable planetary system. That assembly is violent. Planets collide, orbits shift, comets are scattered, dust is ground down, giant planets migrate and redirect smaller bodies. A single large planet in the wrong place can eject material, deliver ice inward, destabilize terrestrial worlds, or shield an inner system from some impacts while causing others. Beta Pictoris allows us to study that stage directly. When you look at Earth now, the solar system appears orderly. The planets follow predictable paths, the sky seems permanent. But our system was once surrounded by debris, filled with collisions, and shaped by giant worlds exerting gravity across enormous distances. You are living inside the quiet result of an ancient period that looked more like Beta Pictoris. The hidden planet matters because missing one giant changes the story of everything around it. If astronomers tried to reconstruct our young solar system, but somehow failed to include Neptune, the outer debris belt would look confusing. Comet populations would seem wrong, resonances would be unexplained, the architecture would not add up. Now apply that lesson to distant systems. A disk may show a gap, a ring may end sharply, dust may clump on one side. Astronomers may build models and find that no known planet can produce the pattern. The temptation is to blame incomplete physics or unusual dust behavior. Sometimes that may be correct, but sometimes there is another planet in the fog, and the method used on Beta Pictoris d gives scientists a new way to look. This affects the search for environments where Earth-like planets could survive. Giant planets are not automatically good or bad for habitability. Their effect depends on mass, orbit, eccentricity, timing, and the structure of the system. To understand whether rocky worlds can form and remain stable, astronomers need a complete census of the giants around them. An unseen Jupiter can dominate a system. An unseen Neptune can sculpt a belt. An unseen world can rewrite the conditions for life without ever crossing in front of its star. So when Webb identifies a planet through carbon monoxide hidden inside a debris disk, it is not only cataloging a remote object. It is improving our ability to reconstruct how planetary neighborhoods become safe, unstable, crowded, or empty. You exist because over billions of years, the architecture around the sun allowed Earth to remain here. That is the personal connection. Not that Beta Pictoris d resembles Earth. It does not. It is a giant, hot, young world. The connection is that its gravity helps reveal how systems become what they become. Now let's talk about what is happening right now. The discovery was announced in July 2026, but the work is not finished. Researchers are continuing to analyze Webb observations to constrain Beta Pictoris d's temperature, atmospheric composition, and orbit. Future measurements should track its motion, test its mass, and determine how strongly it shapes the debris disk. There is a ticking clock, though not the kind that ends in disaster. Young planets cool and fade. Their atmospheres evolve, their disks thin as dust is blown out, swallowed, or ground into smaller particles. Beta Pictoris will not remain frozen in this stage forever. Astronomers are observing a temporary chapter in planetary development, one that will gradually become harder to read. At the same time, Webb's observing life is finite. The telescope operates around the Sun-Earth L2 point, roughly 1.5 million kilometers from Earth, using propellant for station keeping and momentum management. Its science performance remains strong, and mission projections have extended well beyond the original minimum lifetime, but every observing cycle forces choices. Thousands of researchers compete for limited time. That means follow-up observations must earn their place. Beta Pictoris d has a strong case. It offers a newly discovered planet, a benchmark young system, a bright debris disk, multiple known giants, and a method that could be exported to other stars. The key question is whether the technique works only under unusually favorable conditions or becomes a general strategy. Scientists can now search archival and future spectroscopic data for similar molecular barcodes. Targets with bright disks, suspected gaps, or unexplained structures are obvious candidates. The goal is not to stare blindly at every star. It is to combine gravitational clues from disks with chemical clues from spectra. First, infer where a planet may be hiding. Second, search that region for molecules. Third, use the Doppler shift to test whether the signal moves with the system. That chain could uncover planets that conventional imaging has rejected as noise. But there are limits. Spectroscopy requires enough photons. Molecules must produce detectable features in the observed wavelength range. The planet's temperature and atmosphere matter. The star, disk, and instrument all contribute noise. Data processing can introduce false patterns if researchers are not careful. So this is not magic. It is a tool, a powerful one. The next few years will show whether Beta Pictoris d is an exceptional success or the first member of a hidden population. Researchers will compare observations from Webb, the Very Large Telescope, and future extremely large ground-based telescopes. The European Southern Observatory's Extremely Large Telescope is under construction in Chile and is expected to begin science operations later this decade. Its enormous mirror and advanced instruments should sharpen the study of young exoplanets and debris disks. The Nancy Grace Roman Space Telescope will also advance high-contrast imaging technology. Together, these observatories will suppress the star, resolve the disk, isolate the spectrum, and measure the orbit. And somewhere inside those future data may be another world that currently appears to be nothing. A smooth patch, a suspicious gap, a few absorption lines. Remember the opening image, a grain of pepper hidden inside a stadium floodlight. The discovery of Beta Pictoris d means astronomers no longer have to rely only on seeing the grain. They can search for the chemical shadow it leaves in the light. Here is what I want you to take away from all of this. The universe is not empty where our pictures look empty. That is the line. The universe is not empty where our pictures look empty. For centuries, astronomy was limited by brightness. We saw what shone. Then instruments became sensitive enough to detect what dimmed, what wobbled, what bent light, what heated dust, what absorbed a narrow wavelength. Each new method revealed objects that had always been present, but had no obvious image. Beta Pictoris d belongs to that tradition. It was hidden, but not silent. Its atmosphere absorbed carbon monoxide wavelengths. Its gravity shaped surrounding debris. Its motion shifted the spectrum. The planet had been writing its existence into the system long before Webb learned how to read it. There was something humbling in that. Nature does not owe us a clear photograph. Reality can be buried in noise, mixed with glare, spread across wavelengths invisible to human eyes. The answer may not look like an answer until the right instrument asks the right question. And perhaps that is why this discovery feels larger than a single giant planet. It reminds us that ignorance is often not the absence of evidence, it is the absence of a method. Webb supplied the method. Now astronomers will use it. Subscribe for more evidence-driven journeys into the universe, and switch on notifications so you do not miss the next result that changes the map. In the comments, tell me this: how many giant planets do you think are still hiding inside bright debris disks around nearby stars? Share this video with someone who believes every major world near us must already have been found. Because 63 light-years away, inside the glare of a young star, a planet twice the mass of Jupiter spent decades disguised as fog. A grain of pepper inside a floodlight. Not gone, not silent, simply unread, until now. Thanks for watching. https://science.nasa.gov/missions/web/discovers-hidden-planet-star-system/NASA's Webb discovers hidden planet in famous star system, NASA Science.